Today, we're going to discuss the last little bit that we need to learn in this particular unit. All right, today's topic is talking about the fact that we have been throwing around this word ideal gas for this entire unit, right? Do we even really know what an ideal gas is? So we started off with the kinetic molecular theory, KMT, people will throw around. And it has certain assumptions along with it. The first one is gases are constantly moving. As a matter of fact, all particles are constantly moving. All molecules are constantly moving. If any molecule or particle was to stop moving, what would that be called?
Absolute zero.
Absolute zero, which we have not gotten to yet. Next one is gases have negligible volume. Third one is gases do not attract or repel each other. That's the gas molecules. Gases undergo elastic collisions, and gases have an average kinetic energy that is related to temperature. It's not exactly the same as temperature, and we've learned a little bit about that during this unit. So we've been using the kinetic molecular theory to develop what's called an ideal gas. In an ideal gas, particles have no volume, there's no molecular attractions, and they follow gas laws at all pressures and temperatures. Now let's talk about the reality of that, which is real gases as opposed to ideal gases. Real gases, the particles have volume. So when you take the volume of a gas, you're taking the volume of the container that it's in. You're not accounting for the fact that the gases have actual volume themselves, the gas molecules themselves. Real gases also have molecular attractions. The only truly nonpolar molecules are diatomic elements or elements that are compounds that have symmetry. All of the rest of the particles have some sort of polarity. And even when there is no polarity, they do have what's called London dispersion factors, and they attract each other. And real gases differ at low temperature and high pressure. This is what you're going to need to remember. Low temperature and high pressure. How you can remember them is, what would you do to a gas in order to get it to turn to a liquid if you wanted it as a liquid? First thing you would do would lower the temperature. The other thing you could do is increase the pressure. So when you start to impose conditions that might eventually turn a gas into a liquid, that's when they stop behaving like an ideal gas. So at STP, pressure is 1 atmosphere. That's considered low pressure. So we're all good pressure-wise at STP. It's when pressures get a lot higher than that they start to deviate. At STP, the temperature is 273 K. That's considered relatively high temperature. So when we start to get a lot lower than that, then gases will start to deviate from the ideal gas law. So the ideal gas law has some assumptions also that allows us to use all those handy-dandy formulas we've been using. So ideal gases are imaginary gases that perfectly fit all the assumptions of the kinetic molecular theory, meaning that gases consist of tiny particles that are far apart relative to their size. Collisions between gas particles and between the walls of the container are elastic collisions, and no kinetic energy is lost in elastic collisions. I'm going to show you a formula that's going to seem pretty intricate at first glance. And I'm also going to caveat this with, we aren't going to do any plug and chug with this formula. So we're not going to take an input numbers into this formula, but we're going to use the formula to understand the things that we need to know about the ideal gas law. This is called the van der Waals equation. So these right here are called the corrections. Notice these corrections to the ideal gas law are related to the number of moles. And the things that we need to correct right here are pressure and volume. So when we're correcting for pressure, what we're correcting it for is the fact that real gases attract each other. Attract or repel, depending on the case. So this has to do with the polarity of the molecules. We haven't gone into a lot of polarity, so that's going to be in a unit in the future. So we have to correct for pressure to deal with the polarity. Then let's go down here. We also have to correct for volume because real gases have size. So let's go over this. Notice this is specific constants for each gas. The specific constant A is related to the polarity. The specific constant B is related to the volume of the gas. Besides those corrections, notice that this is the ideal gas law. So this is PV on the left-hand side and nRT on the product side. We are not going to use this formula in practice, as in plugging and chugging, but it does give us a lot of information. So this comes from the Deviations from the Ideal Gas Law Pogel. It's like a 7-page packet, which we were going to try to avoid a lot of it, because we're going to go straight for what do I need to know for the AP exam and what do I need to know to understand what's going on here. Okay, so let's keep a framework of what do I need to know for the AP exam, in that we've got to read this graph. You might actually see this graph on the AP exam. It might ask you to analyze it. So we're going to look and we're going to see on the independent axis, or the x-axis, we have the volume of the gas. That's the one we control. On the y-axis is the dependent axis, and we are measuring the pressure in relationship to the volume. Now let's pick out the individual gases. This right here, this line right here, is ideal. This one right here is helium, neon, argon, and krypton. So what's happening here at a very low volume, at a small volume? Notice that krypton's not even on this graph. That's because if you tried to jam the same amount of gas in there of krypton, it would actually not be a gas anymore. So this is the one that we're discussing, the effect of the size of the molecules. So helium's very small, and then neon, and then argon, and then krypton. So krypton and argon are behaving the way they are, especially krypton, because they're large molecules. So at high pressures, those gases have lots of attraction. Now notice none of them are polar molecules. But what happens is the larger the molecule, the more instantaneous dipole that they could have, which is called London dispersion forces. It is more of a chance that the electrons could induce a temporary dipole. So this is one where you'd look at it and be like, krypton is behaving this way because it is a big molecule. The larger the molecule, the greater the intermolecular forces. And we're going to learn all about IMFs later. The smaller the molecule, the weaker the intermolecular forces. So this would be a graph that would be representing the correction to the ideal gas law that is related to volume. Let's go to the second graph that's in this POGO, the deviation from the ideal gas law POGO. Next one has to do polarity, and polarity is going to be something that we didn't really go over in great detail yet, but we will. So this in the middle here is the ideal gas law. An ideal gas, a gas that's behaving completely ideally. Notice how close hydrogen is. And the reason that hydrogen is so close to behaving ideally because it's very small. Therefore, you don't have to make a lot of correction to the volume for hydrogen because of how small it is. It's also a diatomic element, so it is completely nonpolar. So it's going to have super small intermolecular forces. So this is small and nonpolar, meaning that it has weak IMFs and small volume. Then next is going to be carbon dioxide. Remember we drew carbon dioxide on the board the other day? And carbon dioxide has no lone pairs on the central atom. Therefore, it is symmetrical. It is a linear molecule that's symmetrical, so it is nonpolar. So this is CO2, which is also nonpolar, not particularly small. So it's got weak IMF, maybe medium volume. Compared to the other gases, that is. You're going to have some huge gases some places, but this next one is HCl. HCl, or hydrogen chloride gas, is a polar molecule. So therefore, there's going to be attraction between molecules. So it's going to have greater intermolecular forces than the other two, which is hydrogen and carbon dioxide. That's why they're behaving differently. Same thing with NH3, which is ammonia. Ammonia is a polar molecule. So it's going to have, it's even more polar than HCl. NH3, actually what's called hydrogen bonding. So this is a polar molecule. These are nonpolar up top, and this one is polar. So it has its intermolecular forces is dipole to dipole. So they have a dipole based on the difference in electronegativity of the elements. Him down here, he is very polar. so polar that he has hydrogen bonding. Remember, I don't really like that because it's not really a bond, it's an intermolecular force. But I can't change the world, so that's what everybody's going to call it. You might want to remember to identify hydrogen bonding. Hydrogen bonding is fun. So hydrogen bonding occurs when hydrogen's bonded to either fluorine, oxygen, or nitrogen. So that's what I mean by fun. F-O-N. Those are the only three elements that can be bonded to hydrogen and produce hydrogen bonding. That's because they're small and highly electronegative, and it leads to an increased level of dipole. So this is the greatest intermolecular forces. Still all about the same size, within reason. So that's how you read this. At high pressures, the polar molecules don't behave ideally at all. The nonpolar ones still do. The level of behaving like an ideal gas as a relationship to the polarity will increase as the volume increases, because the greater the volume, the more space between each particle. So let's talk real quick about what's going to be expected of you on the AP exam. On the AP exam, they might say something like, which would behave more ideally at certain conditions. Argon or xenon. You would say argon would behave more like an ideal gas because it is a smaller molecule. They're both not molecules, they're both atomic gases. The other thing they might say to you is which would behave more like an ideal gas, HF or HCl. HCl would behave more like an ideal gas because HF is more polar. HCl does not have hydrogen bonding because it's not part of fun. HF does have hydrogen bonding because it is part of fun. So it's less polar and it has weaker intermolecular forces. So basically what you need to grab out of here is they're going to talk to you. They're not going to ask you to plug anything into that formula, but they're going to talk to you about the conditions that arise that would cause a gas to behave less like an ideal gas. That would be high pressure, low temperature, larger the molecule, and more polar the molecule. Those are the conditions that you want to have in the front of your mind. So this concludes the lecture on deviations from the ideal gas law.